All right, let's think about surjective functions. So remember that injective functions map distinct inputs to distinct outputs. Surjective functions guarantee that for every possible output, there is an input. So the definition of this would be, we say f from A to B is surjective if for all B and B, so for every possible output, every element of the codomain, there exists A and A such that f of A equals B. Okay, so let's go back to our example where we have some simple sets where we can depict the functions via arrows moving from one to the other. So we'll call this A and B. Let's say A has A, B, C, and D, and B has E, F, G, and H. So if I have that maybe psi of A equals E, psi of B equals F, psi of C equals H, and psi of D equals G, well, if I give you F, you can tell me B maps to F. If I give you C, you can tell me, if I give you H, you can tell me C maps to H. Whereas if I were to instead define a function, let's call it A, B, C, D again, E, F, G, and H. If I say that A maps to E, B maps to G, C maps to G, and D maps to H, well then I could say, let's look at F. Can you give me some element of A, which is going to get sent to F under our function, maybe this time it'll be Z, and you can't. So here, psi is surjective, and Z is not surjective. All right, let's once again think about the function f of x equals sine x, going from sort of an unspecified domain A to an unspecified domain B, codomain B. So why don't we think about how we can choose our domain A such that when our codomain is the interval 0, 1, then f is surjective. So let's look at the graph, and we'll draw what we want the range of f to be. Okay, well, notice that sine of 0 is 0, sine of pi over 2 is 1. So when we set A to be 0 through pi over 2, and we apply f to all these elements, then we're going to recover the entire interval 0, 1 as our range. So in this case, for A is the interval 0 through pi over 2, our function sine of x is surjective. Now, what if we restrict the range of our function to the interval negative pi through pi? And we want to choose a codomain B such that this function is surjective. Well, notice that the biggest value that this function takes is 1, and the smallest value that the function takes is negative 1. And it's going to take every value in between 1 and negative 1 on this particular domain. So when B is negative 1, 1, f is surjective. Okay, can we choose B such that f from negative pi to pi to B is not surjective? Well, notice that because the minimum value of f is negative 1, the maximum value of f is 1. If I give you 1.1, then we will not be able to find any input value that's going to get sent to 1.1. So we could say B equals set of real numbers. B equals negative 1, 1 union just 1.1. We just need one element for which no input will get sent to that element to get that the function is not surjective. Let's do a simple proof involving surjective functions. So I'm going to reiterate this again. Before you actually start writing the proof, what you should do is you should look for the relevant definitions, and you should write those definitions so that you can use them as a reference. So in this case, the only important definition is that of a surjective function. So let's, before we start proving anything, write that for a general function psi from x to y, psi is surjective if and only if for all y in y, there exists x in x such that f of x equals y. So every possible output of the function is obtained by the function, right? Okay? Now remember, when you actually start the proof, you should always just rewrite the assumptions you're making and then write what you're trying to show. So we're supposing that we have a function f from a to b and g from b to c such that they're which are surjective. Okay, and we want to show that the composition of g and f is also surjective. So let's re-express what we're trying to show in this more mathematical form by using the definition. So I dot E, we need to show for all C in C, there exists A in A such that G composed with F of A equals C. Okay. So here is where we need to start utilizing our assumptions. So we know, well, we care about an arbitrary element of C. So why don't we say, let C in C be given. Okay, then we can use our assumptions. So we know that G from B to C is surjective. So since G is surjective, there exists some B in B such that G of B equals C. Okay, well now we have an element of B, which is the codomain of F. Since F is surjective, there exists A in A such that F of A equals B. Well now, let's just apply G to both sides of this equation. So note that G composed with F of A equals G of B, but we chose B such that G of B equals C. So we've shown that for any C in C, there exists A in A such that G composed with F of A equals C. And we're basically done. We just say, thus, G composed with F is surjective. And we finish the proof. So think about the steps that I went through to prove this. Hopefully you tried it on your own first. Let me know if you have any questions, and keep an eye out for more videos on this topic.